So in this video we're going to discuss how you can show the theorem that if inscribed angles of a circle are subtended by the same chord, then the angles themselves will be congruent. So what I have drawn here is circle AB with various points located on it, along with a list of statements and reasonings behind them for the formal two-column proof. Okay. In order to do this, we actually need to construct two inscribed angles that go to the same chord. We're going to create that chord by going through points B, C, which I will do right now. And then creating those inscribed angles by going from point E to B and E to C. That's the first angle. And then from E to C is the second angle. Okay. Similarly, we'll go from D to B and D to C as well. We will call this angle here alpha, and we'll call this angle here beta. Right now we're suggesting that these two are the same, but since we don't know that for certain, I'm just going to mark this with a second hashed line in order to suggest that maybe they might be different if we find something during this proof. Okay, so we start with what are our givens. First, we have the circle AB. We have given angle alpha and given angle beta, along with the chord BC. Okay. So these are our givens for this particular situation. We're now going to attempt to again demonstrate that alpha and beta are congruent because they subtend, or they mark out, the same chord BC. Okay, so this is our given statements right here. Okay. In order to do this proof, we're actually going to draw two additional lines. We're going to create two radii from A to B and A to C. Okay, and this proof actually will end up relying on our previous theorem, saying that when you look at an inscribed angle versus the central angle will always be twice as large as the inscribed one for the same chord. So that's where we're headed with this. So let's draw the central angle right now. From A to C, and A to B, we now have the central angle right here called gamma. Okay. So when we do that, okay, we also notice that AC and AB are both radii. So we can write that AC is congruent to AB because they are radii of the same circle. Okay. Now, because of this and because of our use of the isosceles triangle that we have just created, where two sides are equal, the opposite angles to those must also be equal. Okay, that's one possible way to go about this. The actual preferred way is to merely say that from our inscribed angle to central angle, we know that gamma must be twice what beta is, and that gamma, again being the same central angle to a different inscribed angle for the same chord, must also be twice what alpha is. Okay? So truthfully, these are just the measures that are equal, so the measures themselves are what is equal, twice the measure of beta, twice the measure of alpha. Okay, and this uses the symmetric chord. I'm sorry, it uses the not the symmetric chord. This uses the central angle is twice the double angle. For the exact same chord. Now, when we continue on, we can then say, since the measure of gamma is equal to itself, then we know that twice the measure of beta must be twice the measure of alpha. Do a quick simplification, and then we know that the measure of beta is the measure of alpha, and therefore beta itself must be congruent to alpha. Okay, so this just is substitution. This right here is simplification, and then this at the bottom is a statement of if the measures of two things are the same, then they must be congruent. Okay, and this is what we originally set out to prove, and we have then just proven that if inscribed angles of a circle are subtended by the same chord, BC, then the angles, those inscribed angles, alpha and beta, are congruent.